Greetings everyone. I am CH Maunika, third year Electronics and Communication Engineering student from JNTUH University College of Engineering, Science and Technology, Hyderabad. Today we are very happy to present our internship project titled Real-Time EV Dashboard and ADAS Warning System. This project was completed as part of our internship at Emertxe Technologies, where we gained hands-on experience in embedded systems and automotive electronics. As electric vehicles are becoming increasingly popular around the world, there is a growing need for intelligent systems that can continuously monitor vehicle performance and improve road safety. Traditional dashboards only display basic information such as speed and battery level, but modern electric vehicles require much more advanced monitoring systems. They need to provide real-time information, detect faults, warn drivers about nearby obstacles, and help prevent accidents. To address these requirements, we developed a system that combines an electric vehicle dashboard with an advanced driver assistance system, commonly known as ADAS. Our project uses an STM32 microcontroller, various sensors, UART communication, and a Python-based graphical dashboard to display live vehicle data and generate safety warnings. During this presentation, we'll explain our learning journey throughout the internship, discuss each module we developed, describe the software and hardware tools we used, and finally demonstrate the outcomes and future scope of the project. We hope this presentation gives you a clear understanding of both the technical concepts we learned and the practical skills we developed during this internship. Now let us begin by understanding the objectives and overall structure of the internship. This internship was designed to provide practical exposure to the embedded systems and real-time automotive applications. Instead of only learning theoretical concepts in the classroom, we worked on building a complete embedded project from scratch. The main objective of the internship was to develop a real-time EV dashboard and ADAS warning system. In this project, the embedded hardware continuously collects information from different sensors, processing the data using the STM32 microcontroller, and sends it to a Python application through UART communication. The Python application that then displays the information in an easy to understand dashboard. Throughout the internship, we learned how different hardware peripherals work together. We gained experience in configuring GPIO pins, using analog to digital converters, generating PWM signals, programming timers, reading ultrasonic sensor data, implementing UART communication, and also designing graphical interfaces in Python. One of the most interesting parts of the internship was learning how individual modules gradually combine to form a complete system. Initially, we worked on small programs like blinking an LED, but by the end of the internship, we were able to develop a system capable of displaying live vehicle information, detecting nearby obstacles, calculating time-to-time collisions, and also generating intelligent warning messages. The internship also introduced us to industry standard development tools such as STM32Cube IDE for embedded programming and PixSimLab for virtual hardware simulation. These tools allowed us to test our programs before implementing them on actual hardware. Overall, this internship greatly improved our understanding of embedded system design, debugging techniques, hardware-software integration, and also real-time system development. It also gave us confidence in working on practical engineering projects related to electric vehicles and automotive electronics. Now that we have discussed the objectives of the internship, let us look at how our journey began during the first week. After the orientation, our technical journey officially began with the fundamentals of embedded systems programming. Before developing complex applications, it was important to understand how an embedded system is structured and how software interacts with hardware. On the first day, we were introduced to the internship environment, the project objectives, and also tools that we would be using throughout the internship. We learned about the STM32 microcontroller, which serves as the brain of our project. Unlike a normal computer processor, the microcontroller is specifically designed to control hardware devices efficiently while consuming very little power. It is widely used in automobiles, medical devices, industrial automation, robotics, and also consumer electronics. The instructors also explained the overall workflow of the internship. We understood that instead of building the entire project at once, we would first learn individual concepts like GPIO, ADC, timers, UART, and sensors. Later, these concepts would be integrated into one complete EV dashboard and ADAS system. On the second day, we wrote our first embedded C program, which was the LED blink program. Although blinking an LED may appear to be a very simple task, it is considered the hello world of embedded programming. It teaches us how to configure GPIO pins, initialize the microcontroller using all libraries, and also control external hardware through software. When the program successfully blinked the LED, it confirmed that our software was correctly communicating with the hardware. This small exercise also helped us understand the process of compiling code, uploading firmware to the STM32 board, and debugging if errors occurred. Through these initial exercises, we built a strong foundation that prepared us for more advanced topics such as sensor interfacing, communication protocols, and real-time control systems. Once we became comfortable with the basic programming, we moved on to interfacing sensors using analog to digital converters, ADCs, and ultrasonic sensors. The next phase of our internship focused on learning about two important peripherals used in embedded systems: the analog to digital converter, commonly called ADC, and the ultrasonic sensor. Let us first understand ADC. Many real-world sensors produce analog signals. For example, a temperature sensor, light sensor, or potentiometer produces a continuously varying voltage. However, a microcontroller cannot directly understand analog voltages because it only works with digital values represented as binary numbers. This is where the ADC becomes important. The analog to digital converter converts the continuously changing analog voltage into a digital number that the microcontroller can process. To understand this concept practically, we connected a potentiometer to the STM32 board. By rotating the potentiometer knob, the voltage changed continuously. The ADC converted this voltage into numerical values, which were displayed on the computer. This experiment demonstrated how accelerator and brake pedals in electric vehicles can be represented using analog sensors. The second part of this module introduced us to ultrasonic sensors. These sensors are widely used in parking assistance systems and obstacle detection in modern vehicles. The working principle is very interesting. The sensor first transmits ultrasonic sound waves that are beyond the range of human hearing. When these sound waves hit an object, they bounce back as echoes. The sensor measures the time taken for an echo to return and calculates the distance using the speed of sound. We programmed the STM32 to continuously measure the obstacle distances in front, left, and right directions. This information later became the foundation of implementing the ADAS warning system. Understanding ADC and ultrasonic sensors taught us how embedded systems collect real-world information and convert it into meaningful data for processing. After learning how to collect sensor data, the next step was controlling the system using timers and PWM signals. Once we understood how sensors provide information, we moved on to controlling different components using timers and pulse width modulation or PWM. Timers are one of the most essential peripherals in any embedded system. They help the microcontroller perform operations at precise time intervals. Without timers, many applications such as motor control, communication, and sensor measurements would become inaccurate. During this module, we learned how to configure different timers available in the STM32 microcontroller. We also studied interrupt-driven programming, where the processor automatically responds whenever a timer reaches a specific value. This allows the microcontroller to perform multiple operations efficiently without continuously checking the timer status. The next concept was pulse width modulation, commonly known as PWM. PWM is a technique used to control the amount of power supplied to the electrical devices, especially motors. Instead of continuously varying the voltage, PWM rapidly switches the power on and off. By changing the percentage of on time, known as the duty cycle, we can control the average power delivered to the motor. For example, a low duty motor cycle results in lower motor speed, while a high duty cycle increases the speed. This method is highly efficient because very little energy is wasted as heat. Using these concepts, we developed a simple electric vehicle control module. The vehicle was designed to operate in three driving modules. That is, the first mode was eco mode, which focuses on maximum battery efficiency by reducing power consumption. The second was normal mode, which provides a balanced combination of performance and efficiency for everyday driving. The third was sport mode, where maximum motor performance is achieved, although battery consumption increases more rapidly. We also simulated battery discharge based on the selected driving mode and estimated the remaining driving range. This gave us better understanding of how modern electric vehicles manage energy efficiently while providing different driving experiences to the user. This module was particularly exciting because it connected the theoretical concepts of timers and PWM to real-world automotive applications. After understanding vehicle control, the next stage was integrating timers with ultrasonic sensors to develop intelligent ADAS functionality. This will be explained by the next teammate, Grishma.
Hello everyone, this is Grishma. I will be continuing the presentation. After learning about timers and ultrasonic sensors separately, the next step was integrating them into one system. The timer was used to generate accurate delays, which helped the ultrasonic sensor measure obstacle distances correctly. Once this integration was complete, we implemented the basic functions of ADAS or Advanced Driver Assistance Systems. ADAS is designed to improve vehicle safety by detecting nearby obstacles and warning the driver before a collision occurs. In our project, ultrasonic sensors continuously monitored the front, left, and right sides of the vehicle. Whenever an object came within a certain distance, the system detected it and generated a warning. This information was then sent to the Python dashboard where the driver could see alerts in real time. This module helped us understand how different embedded peripherals work together to build intelligent vehicle safety systems. After implementing basic obstacle detection, we made the warning system smarter by introducing timer to collision calculations. A reliable embedded system should be able to detect faults and respond safely. In this module, we implemented fault management where the system continuously monitored important parameters and reported any abnormal conditions such as sensor failures or communication errors. We also learned about the finite system machine or FSM. Instead of performing every task at once, the system operates in different states like parked, ready, driving, regenerative braking, and fault. The system moves from one state to another depending on the vehicle's condition. For example, when the vehicle starts moving, it changes from ready to driving. If a major fault occurs, it automatically switches to fault mode for safety. Using FSM made the software more organized and reliable, which is why this method is commonly used in automotive systems. To monitor and test all these functions easily, we used UART Communication. UART stands for Universal Asynchronous Receiver Transmitter, and it is one of the most commonly used communication protocols in embedded systems. In our project, the UART shell allowed communication between the STM32 microcontroller and the computer. Instead of changing the program every time we wanted to test something, we could simply send commands through the UART terminal. Using the shell, we monitored live vehicle parameters, changed settings, injected test faults, and displayed the system status for debugging. This made testing much faster and helped us identify problems more efficiently. It also gave us practical experience with serial communication, which is widely used in embedded and automotive applications. Throughout these activities, we developed several technical skills that are important for embedded engineers. The final stage of our internship was developing a Python-based dashboard to display the data collected by the STM32 microcontroller. The dashboard acts as an interface between the vehicle and the user. Instead of viewing raw numerical values, the driver can easily understand the vehicle's condition through graphs and warning messages. The STM32 continuously sends vehicle data such as speed, battery, acceleration, motor, temperature, and obstacle information through UART communication. The Python program receives this data and updates the dashboard in real time. The dashboard also displays ADAS warnings and fault messages whenever necessary. This allows the user to quickly identify problems and take appropriate action. Overall, the Python dashboard made the system more user friendly by converting technical sensor data into clear and meaningful visual information. Throughout this internship, we gained practical knowledge in many areas of embedded system. We learned the fundamentals of embedded programming, GPIO, configuration, ADC programming, timers, PWM, UART communication, and sensor interfacing. We also understood how ultrasonic sensors are used for obstacle detection and how ADAS features like time to collision improve vehicle safety. Apart from embedded programming, we gain experience in Python dashboard development, real-time data visualization, debugging, and hardware-software integration. Overall, this internship helped us improve both our technical knowledge and practical skills, giving us a better understanding of how modern electronic vehicles are designed and developed. Before moving to the dashboard, let us first understand what an embedded system is. An embedded system is a computer designed to perform a specific task within a larger device. Unlike a personal computer, which can perform many different functions, an embedded system is built to carry out one dedicated job efficiently and reliably. Examples of embedded systems include washing machines, microwave ovens, smartwatches, medical equipment, traffic signals, and automobiles. In modern vehicles, embedded systems are responsible for controlling functions such as engine management, braking systems, airbags, and dashboard displays. Our project is also an embedded system because the STM32 microcontroller continuously collects data from sensors, processes it, and sends it to the dashboard for real-time monitoring. This allows the driver to receive important information instantly. Understanding embedded system helped us realize how hardware and software work together to perform real-world applications. Now I hand over the presentation to my teammate Harshita, who will explain the remaining modules, software tools, dashboard design, and the future scope of the project.
Hello everyone, I am Harshita. One of the main software tools used during the internship was STM32Cube IDE. STM32Cube IDE is an integrated development environment that allowed us to write embedded C programs, configure peripherals like GPIO, ADC, UART, and timers, and debug our programs. It also provides CubeMX, which makes peripheral configuration much easier by allowing us to configure hardware settings graphically before generating the code. Another useful tool was PiximLab. PiximLab is a virtual hardware simulator that allowed us to test our programs before implementing them on actual hardware. Using simulation helped us identify programming mistakes, communication errors, and logic issues without risking damage to physical components. These tools made the development process faster and more efficient while improving our debugging skills. After developing the firmware, we designed the architecture of the Python dashboard. Python dashboard, GUI architecture, and integration. The Python dashboard was designed using a modular architecture where different parts of the program handled different responsibilities. One module received the serial data sent by the STM32 microcontroller through UART. Another module processed the received data, while the visualization module displayed using graphs, gauges, and warning indicators. The dashboard continuously updated the vehicle information in real time without requiring any manual refresh. Another important feature was the integration of ADAS logic into the dashboard. Whenever the system detected an obstacle or calculated a dangerous time to collision value, the dashboard immediately displayed a warning message. This modular design made the program organized, efficient, and easy to maintain. Now let's look at the final appearance of our dashboard and the ADAS alerts displayed to the user. Dashboard design, night mode telemetry. The dashboard was designed using a night mode interface, making it easy to read even in low light conditions. The speedometer is displayed prominently so that the driver can quickly check value speed. Thus, battery status shown using a state of charge indicator, while additional information such as motor temperature, acceleration, torque, and driving mode is displayed clearly on the screen. Graphs are also included to show changes in vehicle speed over time, allowing users to observe driving patterns. The dashboard uses different colors to represent different conditions. Green indicates normal operation, yellow represents caution, and red is used for critical warnings or faults. This color coding helps the driver to understand the vehicle status at a glance. Overall, the dashboard provides all the information in one place, making vehicle monitoring simple and effective. ADAS alerts examples. This slide shows how main ADAS feature implemented in our project. Blind spot left, blind spot right, and forward collision warning. The blind spot detection system uses ultrasonic sensors to monitor the left and right sides of the vehicle. If another vehicle or obstacle enters the blind spot, the system immediately alerts the driver. The forward collision warning features measures the distance to the object ahead and calculates the time to collision or TTC. If the vehicle is approaching too quickly, it generates a warning to help prevent accidents. These features demonstrate how embedded systems can improve driver safety by providing timely alerts.
Okay, now let us look at the visual working of our project. For that, first we open command prompt running as administrator and type in the following command to open our Python dashboard. Python and then enter. Now we got our Python dashboard showing us a speed and alarm mode. Now this is the none condition where the front is 252, left is 148 and 152. No lights are on, red or blue. Now we have seen the none condition. To change it to advisory, we okay first let us change it to critical. We change it to something below here. You can see the red light turning on and also decrease the right somewhere around 30. You can see the green light also turning on. This is the critical condition as you can see. And next, let us get advisory condition. For that, let us increase the front distance. The LED light is turned off and then decrease the left distance to a very low value. As you can see, the blue light is now turned on and then increase the right value to somewhere around here. Now we got the advisory condition. This is the working of a Reefy dashboard project. Although a project is a working prototype, there are many possibilities for future improvements. One enhancement is CAN bus integration, which would allow communication with different vehicle systems. We can also use cameras for advanced features such as lane detection and traffic sign recognition. Artificial intelligence can be added to predict driver behavior and improve safety. Cloud connectivity, mobile applications, and voice control can make the system more user friendly and suitable for real world electric vehicles. Now I'll conclude our presentation by summarizing what we have learned. This internship gave us valuable practical experience in embedded systems and automotive technology. We successfully developed a real-time EV dashboard with an ADAS warning system using STM32, embedded C, UART, and Python. Through this project, we learned sensor interfacing, UART communication, fault management, real-time data visualization, and also software-hardware integration. Overall, this internship improved both our technical knowledge and practical skills, preparing us for future projects in embedded systems. Finally, we would like to thank everyone who supported us. We sincerely thank Emertxe Technologies for providing us with the internship opportunity. We also thank our project guide, mentors, and faculty members for their continuous support and guidance throughout the internship. This experience helped us apply our classroom knowledge to a real world project and develop valuable technical skills. Thank you all for your time and attention. This concludes our presentation. Thank you for your patient listening. We would be happy to answer any questions or clarify any part of our project. Thank you once again.